All right, so the lesson today is on calculations of heat exchange in mixtures, 8.5 in your physics text. It's for physical science 20. So what I'm talking about is if we have a certain amount of energy represented by mc delta T, and it's lost by one thing or one material, then that same amount of energy is going to be gained by another material. So if something loses energy, that energy has to go somewhere. And so this is the algebraic kind of expression there. This is the explanation there. So whatever energy is lost by something, it has to be picked up by something else. Here's a sample problem that you will have to work with and to know how to do in this section. And it's sort of, I just summarize it here, it sort of reads like this. A 0.5 kilogram sample of lead is at 100 degrees Celsius, and it's placed in 0.2 kilograms of water at 20 degrees Celsius. This is also contained in an aluminum calorimeter with a mass of 0.4 kilograms. The final temperature of all materials is 24 degrees. Find specific heat of lead. All right, it might be helpful to draw a picture. I always draw a picture whenever I can. And let's say this is sort of our calorimeter. You know, it's a fairly sealed unit here. And inside this aluminum, okay, here's the aluminum body. Inside we have some water, and we also have a piece of lead in here, okay, Pb. Now the lead is really, really hot. See, it's a hot piece of lead, and it is placed inside this calorimeter. Now, because this piece of lead is so hot, it's going to be giving away heat, right? And what's going to be picking up the heat? Well, the water and the aluminum. Right? So the water here and the aluminum body of this calorimeter is going to be picking up the heat. Okay, so we got hot here, we got cold here, and it's all going to level out. All right, and so the lead here is going to be dropping temperature, and so therefore it's going to be giving off heat. It's going to be passing its heat to something else. And what's going to pick up the heat? Well, we actually have two things here that's going to pick up the heat, and that is the water and the aluminum body calorimeter. So this is how you set it up. You set it up with this equation right here. And we're going to say what's losing heat is the certain mass of lead, and that's going to be the specific heat of lead, which we are trying to actually find here. That's what we're finding. Okay, and it's going to change a certain temperature. And what's going to pick up that energy is water plus aluminum. And of course, the energy that's picked up, it's expressed as this expression right here. Mass times specific heat times change in temperature. So that's what we've got. So if we fill in all the values that we are given, then we've got something that looks like this. The only thing that you might be wondering about is this right here. Okay, and this temperature change right here. Let me just explain that. How did I get those values? Well, the lead started off at 100 degrees Celsius, and it went down to what? Well, it doesn't say what the lead is, does it? But what it does tell us is that the final temperature of all materials is 24 degrees Celsius. Now, in this situation, and in any situation where you have a really hot, high energy object and a cool environment or another cool object that it's coming in contact with, when all is said and done, at the very end of things, they are going to settle on some equal temperature. So they're going to pass energy back and forth until they are equal in the amount of energy they have. That's kind of a settled sort of ground, nice, comfortable state for everyone. So all of these materials are going to have the same final temperature. And so 100 goes down to 24. That is a delta T of negative 76. Okay, 100 down to 24. And that goes right here for the lead, negative 26. It's a drop in temperature. And for the water, it started off as 20, and it went up to 24. So that's why we have a positive temperature change of the water and the aluminum calorimeter. Remember, they started off the same. Everything's going to be the same temperature at the end. So the aluminum calorimeter was at the same temperature as the water. Okay. All right. So now that we've got all these values in, we want to evaluate, and what do we get when we plug all this into the calculator and simplify? This is what it looks like. All right, so if you plug all this stuff into your calculator and you evaluate this portion right here, that comes to 3,360. This portion over here comes to 1,440. And 0.5, negative 0.5 times negative 76 is 38. We solve now for the specific heat here of lead, and we get a number of 126.32. So that's an example of how you could solve a problem like this, where you're looking for just one part of this big long equation, because again, you're given, or you can find all of these other values. I should mention that the specific heats of water and aluminum came from the specific heat chart, so we just looked those up. They weren't given in the question, but we looked those up. And yeah, you'll find that sometimes there's just one thing giving off energy and one thing accepting, but in this case we had both the water and the aluminum that comprised the calorimeter. And we had to use two different expressions because, of course, the amount of heat that the water will absorb and the amount of heat energy that the aluminum will absorb are different. And so we had to take into account and calculate those separately. So that's the sample problem, page 239. And if you are in my class here from your heat physics textbook, if that's the one we're using right now, then here is your assignment here for E equals mc delta T and the heat exchange and mixtures assignment. But anyways, I hope you learned something from that sample problem. And that's how you calculate heat exchange and mixtures.